Welcome back to Math 104. We are discussing the game involving the unfair four-sided die. We've concluded that its average payoff per play of the game is $4.50. The question is, would you play this game once at a cost of $4.75? Just for the fun of playing the game, it might be worth playing once, but not as a way to plan for your financial future. You can't lose more than $2.75 even if you get really unlucky, right? You could roll a 1, you could receive $2 but then have to pay $4.75, so at worst you lose $2.75. Okay, big deal. You might have had fun playing. But when you play the game 100 times at a cost of $4.75 per play, well, now we're starting to see some of the long-term behavior, so that you are unlikely to be lucky enough to make money on 100 plays of the game. It could happen. It's possible that you could roll a 4 100 times in a row. It could happen, but it's very unlikely. In the long run, this game is a losing proposition, and 100 plays of the game are enough repetitions to be a bad idea financially. What is the greatest amount you would be willing to pay per game to play a very large number of times using this unfair die? If you pay anything less, strictly less, than $4.50 per game, then you will make money in the long run. You will have wins and losses along the way, but in the long run, it will average out to a profitable game for you. The $4.50 that you're receiving on average, minus anything less, will be a positive number, a net gain. If you pay exactly $4.50 per play of the game, you will break even in the long run. That is, you will neither make money nor lose money. This is because, in the long run, you would be receiving $4.50 per play of the game, on average, but also paying $4.50 per play, and therefore your net gain would be $0. This could be a good way to set up the game if you're playing with friends just for fun, for example. If you pay anything more than $4.50, you will lose money in the long run. Every casino game has been analyzed mathematically, and it's been set up so that in the long run, it is profitable to the casino, which means that it is a losing proposition for the customers. One of my goals for this course is to persuade you not to gamble, because gambling is usually rigged against you. The conclusion here is that computing the mean of an ideal dataset plays an important role in using probability to make decisions about whether it's a good or bad idea, for example, to play a certain game. Let's take a closer look at the die rolling game. Within the game, every outcome has two numbers attached to it. One number is a certain value associated with the outcome. In this case, a monetary payoff, but we will see non-monetary examples as well. So the outcomes were 1, 2, 3, and 4. The associated values were $2, $4, $6, $8. For each outcome, there was a dollar amount associated with it. And then the other number attached to the outcome is the probability that that outcome occurs. Given such an experiment, that is, an experiment set up with this kind of information, as in our die rolling game, we can write down an ideal data set of the associated values. In our example, it was the dollar values, the monetary payoffs. The mean of such an ideal data set is called the expected value of the experiment. The expected value is, in the long run, the average associated value per run of the experiment. So in our context, or more generally the context of games with monetary payoffs, the expected value, as we're calling it, is the average payoff in dollars or other currency per play of the game. Now here's an important caution. The expected value is not the most likely value. In fact, it's not even possible in this die-rolling experiment for $4.50 to be the payoff of a one-time play of the game. It's just not one of these numbers. It's the long-term average value of what you'll receive if you keep playing the game, but it is not a value that you could receive on any one play of the game. Right now, we're just going to think about the payoffs themselves and not worry about what it costs to play. We can ask, if you play this game 100 times, what are your expected total winnings? This is mercifully straightforward. An average of $4.50 per play of the game times 100 plays equals $450. We can express this by saying your expected winnings are $450. Now, why does this language of expected make sense here? It conveys that before you set out to play 100 times, although there is uncertainty about what exactly will occur, there is also some predictability in the sense of long-term averages. In a certain sense, when you go to play 100 times, you expect to receive $450. What that really means is that on a truly average day of playing 100 times, you will receive $450. The word expected is a technical mathematical term, and in this context, it has a technical meaning. Note the difference between the expected value of the experiment of rolling the die and observing the number that appears, and the expected value of the game, that is, of the experiment of rolling the die and finding the payoff in dollars. In the first case, the outcomes are 1, 2, 3, and 4, and the associated value is just that same 1, 2, 3, or 4. Here, the ideal data set of values is exactly this: 4 copies of 1, 3 copies each of 2 and 3, and 2 copies of 4. Those are the values whose average is the answer to this question. When you roll the die and just look at the number that appears, what number do you expect in this sense of what is the long-term average? That's computed as 4 copies of 1 plus 2 3 times, plus 3 3 times, plus 4 2 times, all divided by how many numbers there are. Averaging those up comes out to 2.25. When you roll this unfair die and average the results, then over a long period of time, it turns out that the average will be 2.25. The fact that 2.25 is not itself a number that can appear when you roll is not a problem. It's just an average. It's an average that reflects the fact that the probabilities are weighted more heavily toward the low end of the sample space, so that the 1s contribute more heavily than the 4s do to the average. The second expected value pertains to the dollar amounts, and we've already done this computation and found by averaging up all 12 dollar values that can occur that the average is $4.50. So expected value is just new terminology. It's a new mathematical name for what we have been computing as the average value, the mean value of an ideal data set. Here is a definition of expected value, more typical of how it appears in mathematics textbooks. Suppose that an experiment has a sample space with n possible outcomes, not necessarily equally likely. Please do not panic at the sight of a letter instead of a number. I don't want you to have a panic reaction to memories of your algebra classes. It just means that however many outcomes there are, we call that number n. Suppose further that each outcome has a certain value associated with it, such as a dollar payoff. In other words, we're talking about the kind of experiment, the kind of setup where we've been computing expected value. Then the expected value of this experiment equals the following long sum. It's the value associated with outcome number 1 times the probability of outcome number 1, plus the value associated with outcome number 2 times the probability of outcome number 2, plus the value associated with outcome number 3 times the probability of outcome number 3, etc. We keep computing value times probability until we get up to the last outcome in the list. And we add the value associated with outcome number n times the probability of outcome number n. In order to compute the expected value by this definition, relentlessly multiply value times probability plus value times probability plus value times probability. Keep going and be sure to do this for every outcome, and finally compute the sum of all of these products. It's crucial to include all the outcomes of the experiment in this computation. A common error is to do only part of the computation, but leave out some of the outcomes. Expected value is essentially a weighted average of the associated values, where the values are weighted by their probabilities of occurring. The outcomes with higher probabilities count more heavily in the sum because they have a higher weight, and the ones with a lower probability count less heavily in the sum. They are weighted less heavily. We will see more clearly what this means when we do a computation. As an example, let's apply the definition to find the expected payoff of the game in which you roll the unfair four-sided die and receive twice as many dollars as the number appearing on the die. Again, we're forgetting for the moment about any kind of cost to play the game. We're just looking at the expected payoff. I'm just going to do what the definition tells me and compute value times probability that we obtain that value plus value times probability that we obtain that value plus $6 times probability that we receive $6 plus $8 times probability that we receive $8. I'm not dividing by anything here. Any division I might have needed to do is already built into the fractions themselves. If I go and compute this, then lo and behold, I get exactly $4.50. We have two different definitions of expected value, two ways of computing it, and, good news for us, they produce the same answer. In order to appreciate why they produce the same answer, I'd like to do some algebra and manipulate this expression right here. I can write this as $2 over 3 plus $4 over 4 plus $6 over 4 plus $8 over 6. Right? $8 times 1/6 is nothing other than $8 divided by 6. Now what are you dying to do? After all your years of mathematical training, you can't wait to find a common denominator, and that common denominator will be 12. And why do you need a common denominator? So that you can add up the fractions. So how do I transform each of these fractions to make 12 the common denominator? I have to take my $2 and multiply by 4. If I'm transforming 3 into 12 by multiplying by 4, I also have to take the numerator and multiply it by 4. How about the next fraction? The denominator results from multiplying 4 by 3, so the numerator must be the result of multiplying $4 by 3. Similarly, in the next fraction, the denominator is the result of multiplying 4 by 3, therefore the numerator is the result of multiplying $6 by 3. And finally, 12 is the result of multiplying the denominator 6 by 2, therefore we must multiply the numerator 8 by 2. The whole point of this was to be able to add the fractions, which is to say, add the numerators, all divided by the same common denominator. So I'm writing out that great big numerator, and I divide by my denominator of 12. Let's ponder that expression for just a moment. Before going on to the next video, answer the following question. Where have you already seen the expression we just obtained in the numerator of this expected value? You have seen this before, and pretty recently too.